So we're almost in the middle of our second module for this course. The second module dealt with the physicality of quantum physics, how things change with time, what does the dynamics look like, and we're trying to get a more physical flavor of quantum physics. So today I would like to move into another very interesting direction. We've looked at the time-dependent Schrodinger equation, and we've seen several examples of the applications of the time-dependent equation. So far so good. So far we've been dealing with psi, ket psi, which is a quantum state. Now this quantum state could be a function of time. That's fine. And how do we know the state evolves with time? The Hamiltonian is the driver for the quantum state. The Hamiltonian drives the state. Just like the force in classical physics drives a classical object, it accelerates the object. In quantum physics, the Hamiltonian drives the quantum state. Now, the central question I would like to ask today is, when someone poses to us the question, where is an object, is a quantum object? How do we answer this? So this centrality of whereness, where is an object? When you look at physics, you often have to deal with location of an object. Where is an object? Where is the earth? Where is the sun? Where is a car at one particular point in time? You throw an object. Want to throw this object, right? You throw it. Where is this object with time? So how do we deal with this question of whereness in quantum physics? So where is an electron? Where is a photon? Electron, neutron, molecule, where is it? You've dealt with electrons in hydrogen atoms. So the electrons take up certain orbitals. What are orbitals? And where is an electron? If you say the electron is in the p orbital, and I ask you the question, where is that electron? What will your response be? So if you learned some quantum physics. So today we're trying to describe this idea of location of an object. So if I were to draw an axis for space or position, and the position variable is x. Suppose there is some quantum object in space and I'm just looking at one dimension, just x, no y, z, just x. At some point in time, I measure the object and I measure its location. So now my measurement is done in the location basis. And I find that the object is at some value of x, say x naught. Now quantum mechanics states that when you make a measurement, you create a new quantum state. So the state had existed somewhere in space, and when I made a measurement, say with a quantum microscope, I find that the object is located at x naught. This object could be an electron or neutron, anything. Now this object is located at x naught. A new state has been created. So I can call that state ket x naught. So after my measurement, this is the new state that I've created, ket x naught. All right. Now what does this state look like? It's that the object has been found to exist at x naught. It's also possible that the object is found to be located at x1, x2, x3 and so on. So any ket x is possible. So I can have any ket x. This is my quantum state after measurement. But in generally, you would like to also ascribe a quantum state before the measurement. So you have polarization of a photon, you have a quantum state, and then you measure that polarization either in the horizontal detector clicks or the vertical detector clicks. So you choose a measurement basis. For a photon, for example, this is your device that kind of splits into two paths. One is a cat H path, the other is a cat V path, and you have detectors over here. So you input a quantum state psi, which is the polarization state, and this detector clicks with some probability. That probability is given by the overlap of the input state with cat H modulus square. This probability is cat overlap with V modulus square. So H and V form your measurement axes, your measurement basis. So this, you're very familiar with this idea. But now you're measuring in the polarization basis as well. Now here we are measuring in a position basis, and there is some quantum state psi before the measurement. So, and I really do not know what psi look. I cannot draw psi. Psi is a quantum state. If you agree with me, I can never draw a quantum state. It's impossible to draw a quantum state because the quantum states don't live in our universe. They don't live in the Euclidean space. So there has to be some psi. This is just a cartoonic representation. Some psi which exists in space. And when I make a measurement, I create a cat x0 or a cat x1 or cat x2 and so on. Now the best way in which I can describe this quantum state is by writing it in a form which looks like a function in space, which means I would like to see how this quantum state appears in space, right? So I would like to write this as a function of x. So what I could do is I could take the quantum state psi, which is a quantum object, and write it in the position space. So I take the overlap with x, with cat x. This is writing this quantum state in the position basis. Now I'm measuring in the position space. So I project the quantum state, the abstract physical object that lives in the quantum space, and project it onto my measurement basis. My measurement basis now comprises all the cat x's, cat x1, cat x2, cat x3, cat x minus 5. In fact, the basis is now infinite. Here I have a basis that comprises two basis vectors, cat h and cat v. So this is a qubit, a two-dimensional space. Now I have a basis which is, number one, continuous. Number two, it's infinite. It's an infinite dimensional space and it's continuous. So far in our course, we've only dealt with discrete systems. Now we're trying to deal with continuous systems, infinite dimensional systems. So this is an infinite dimensional space. X coordinate is infinite dimensional. You can take any value from minus infinity to plus infinity. So now what I do is I take the quantum state psi and find its overlap with my position basis. Now my position basis, there could be infinite number of basis vectors, and I call those basis vectors cat x. X can take any value from minus infinity to plus infinity. Now this turns out to be a number. Of course it's a number because it's an inner product. And this number can be a function of x. Okay, it can be a function of x. So let's call this function psi, the same symbol psi, but without the cat sign, because now it's not a cat, it's a function of space. Okay, so now this is a function of space This function of space is called a wave function. It's one word, a wave function. I'll give you examples of this. You had a question.
How do we define ket psi?
Ket psi. So ket psi is the quantum state corresponding to this wave function. So this is a wave function, is the state written in the position basis. And if I were to answer your question, many students will not understand this. This ket psi is going to be given by all the ket x's. Each ket x has a weight, a coefficient psi x, which is this function, and then I integrate over all space. This is what the ket is, but you don't need to understand this. All right, so this is how you move from ket x to psi and psi to the function. Okay, so any more questions? I'm going to explain this. I'm going to give you a few examples. So the wave function in space, because I'm dealing with space here, there could be a wave function in momentum as well, but right now I'm dealing with space. So when I say wave function, it means wave function in space, but there could be wave function in momentum as well. So the wave function is just the quantum state written in the position basis, and it's a function of space, some function of space. Let me give you a few examples. Suppose I have this x-axis and I define a function, a wave function psi x, and that wave function is complex. It's a complex function. Suppose my function is a, some constant I kx. Is this a ket or a bra? Yes or no? No. It's a function of x. I propose that this is my wave function. First of all, the wave function is complex. It's a complex function, or it's a combination of cosine kx and I sine of kx. Okay, so it's a complex one. So can I plot psi with respect to x? I can't, because it's a complex function, but I can plot the real part and I can plot the imaginary part separately. So if I were to plot the real part of this function psi x, what is that going to look like? It's the cosine function. All right, so let me plot this. And this wave function, this real part, goes from minus infinity to plus infinity. So it's a ubiquitous function. It exists everywhere in space. It's a hypothetical function, and it exists everywhere in space. All right. If I were to plot the imaginary part again with respect to x, imaginary part of psi x of the wave function, what is that? That's sine kx. So I can plot the right. So this is a sine function. Now both of these pictures represent the wave function, both of them. Now how does the wave function tell us where can I find the particle? So just as the quantum state itself doesn't have much meaning, but it's overlapped with something, modulus squared has a meaning. In a similar manner, the wave function alone carries little meaning on its own. What you need to do is you need to take the modulus square of this. So if I take this wave function, now it's a function, not a ket, and I take the modulus square of this, what would I get?
Probability of the
Yeah, but what number would I get? A square. A mod square, because A itself can be complex. I can assume it's real. That's why these plots can be drawn. Now this object, the modulus square of the wave function, has a meaning. This is called the probability density. Probability density. Probability density. What this means, by the way, if for this wave function x, I plot psi x modulus square, what would the graph look like? Straight line, correct? It's a mod square, doesn't depend upon x. You get a straight line. And this straight line kind of tells me what's the probability of finding the location at some point in space. That's why it's called the probability density function. So if I want to find the probability between points x1 and x1 plus some delta x, what's the probability of finding the function whose wave function is this, the particle whose wave function is this? What's the probability that I do a measurement and it turns out that a detector between these 2 points in space clicks, or I'm able to locate the particle somewhere here? And this delta x is, by the way, is a small difference between these 2 points. That probability is given by the area under this curve between these points. Okay? So if I want to find a probability of locating the particle whose function is this between 2 points in space, then that probability is going to be equal to the area under this curve, which is the psi square curve between these 2 points. So it's really going to be equal to psi x mod square. Now this is constant. This is constant, so we are fine. Area in this region is simply delta x. This length is delta x, this height is a square, this is a square delta x. Luckily this is a constant function. If I had a wave function, alright, so let's first focus on this quantity. So a mod square or psi x square, if all of this is probability, right? This is, I'm defining this to be the probability. This is very similar to the concept of taking a ket, finding the overlap with another ket, make an inner product modulus square, that was defined to be the probability, correct? That was a postulate, Born's postulate. Exactly in the same vein, in the same manner, I take my wave function, modulus square it, and multiply it with the interval in space, I get a probability. Okay? So all of this is a probability. So what should be the units of this guy over here? What's the units of this part? Per meter, per distance, because this is distance. So this is a kind of probability per unit length. That's why it's called probability density. Probability per unit length. That's why it's called a probability density or a probability density function. Yes, please.
Sir, in this case, the graph is a straight line, so the phi square is equal to a square, but that will not always be the case.
Right. So this is just a hypothetical scenario. No wave function can be of this kind because you want the probabilities to sum to be 1. So there is just a hypothetical case which goes from minus infinity to plus infinity. Yes, please.
So the units are per meter, if it per meter or per 1/2.
No, it's per meter.
It's way over here and then if we multiply.
So all of this is per meter. So this is probability density, probability per unit length, per unit interval. So psi x square, this thing is the probability density as units of per length, dimensions of per length. Now in this hypothetical example, where is the particle likely to be found? Now first of all, can I ask the question, where is the particle? Now I haven't done a measurement. No measurement has yet been executed. But there is some hypothetical particle that has this wave function. So if I were to ask you, where is the particle? It can be anywhere. Or a better semantics would be, it's everywhere. It's everywhere. You do a measurement, it can be found anywhere. But it will be found at one point in space. So this is just like a big wave, a ubiquitous wave that is spread out in space. Just imagine the interferometer experiment, something that's spread out in space, and when a detector clicks, here a position detector clicks, a camera clicks, a pixel on the camera clicks, you find all of that energy that's delocalized on that one pixel. So all the wave function which was spread out in space is now found to be located at one point, and that's the measurement you do. That's the outcome of the measurement, and all possible x's are probable with equal probability. So uniform probability distribution, because this line is everywhere. So you can find the particle here or here, anywhere, with equal likelihood, because it's a uniform probability distribution function. But suppose the particle is located at this point, x naught, and you're happy, then okay, I found the particle here, but you can't extrapolate and say that the particle was here. It wasn't here. It's just that the wave function collapsed to that point. The same ideas that we've been looking for finite dimensional discrete systems apply here. If I find the particle here, the object here, I can't say that the particle was already here. It could have been anywhere. That depends upon the wave function. So once the particle is located at this point, a new state is created. And that new state, of course, is ket x naught. But what does that x naught look in space as a function? What is the wave function corresponding to the new state that has been created? So I need to take the overlap with x, right? I want to find this quantum state in the position basis. So what is the new wave function? A new state created, a new wave function is created. Corresponding to every quantum state, there is a wave function. Now a new quantum state has been created. I want to find its wave function. So if I were to draw this wave function after measurement, so this is after measurement. So after measurement, if I were to draw the new quantum state, now I'm drawing a wave function after the measurement, and I found the state to be, I found the particle to be here. So what kind of function should I draw?
0, 0, 0, 1, then 0.
You're right. So it's just a function which has a strange kind of appearance. It's a 0 everywhere, and just a spike over here. This is spike here. Spike. Now this is a kind of strange function. It's a non-analytic function. This spike goes to infinity. So mathematically this is represented, this kind of function which is 0 everywhere and it only exists at a point, is called a Dirac delta function, and it's represented as this delta sign. It's a function of x minus x naught. So this is how we define, this is a definition, this is how we define the Dirac delta function, that it's 0 everywhere in space, but it's non-zero only when the argument is 0. So the argument is 0 means x, when x equals x naught, that is at this point in space will this function exist, and at that point in space it will be an infinite spike. Okay. So another property of this Dirac delta function is, this is probably the most mathematical thing I will do in this course, is if I can analyze this function as, suppose I have a kind of function that looks like this. It's called a Gaussian function. Suppose. Now this function has a certain area under it. Suppose that area is 1. The area under this curve is 1 units. Now if I compress this and I want to keep the area the same, I compress this function will get taller, right? If I compress it further, it will get even taller. Taller and taller. So I keep on compressing it so that I compress it to just one point. Then asymptotically in that limit, this function must go to infinity. Okay, there's no other choice. So when it does that, that's called a Dirac delta function. The area under this Dirac delta function is still 1. So if I were to take the integral, area under a curve is represented by integrals. If I were to take the area under this curve, this is going to be 1. So this is a property of the Dirac delta function. Another property that you might use in some other course, is useful to introduce at this point, is that if I take any function of x and multiply it with the Dirac delta function and integrate, can you guess what the result of this integral will look like?
Area under f of x?
No. It's f being multiplied with the Dirac delta function.
This is the function itself.
At what point?
X naught.
X naught, good. It's the function at x naught. Because here the function is being multiplied by this. So you have a big function, you're just sampling that point of x which is at x naught. And that is a constant, so you take it out of the integral. And so these are two important properties of the Dirac delta function. Anyway, let's come back to this example. So the probability density function is defined as the modulus square of the wave function. Let's look at a more realistic wave function. This wave function, by the way, corresponds to what is called a free particle. A free particle is a particle that is not influenced by anything else. It's in vacuum. It's not influenced by anything else. It doesn't see any force, any potential energy. Right? So like a photon moving in space or an electron moving in space. Okay? Such a particle, if it's moving at slow speeds, it's going to have an energy which is its kinetic energy. No potential energy. So its kinetic energy is p square over 2m. P is the momentum of the particle. Okay? So these are formulas that you should remember. This you already know. The other property you know from A-level physics is that associated with every particle there is a wave. That is in fact the wave function. So, and the wave and the momentum are related. P equals h bar k, or h over lambda. We also know that for a free particle which is in vacuum, we can write this expression E is equal to h bar omega. So we'll come to these points in a minute, but the wave function that I write over here, this wave function corresponds to a free particle. It's a hypothetical particle, and the probability density for this particle is uniform. It's the same everywhere in space. You can locate it anywhere in space. But the problem with this is, why is it hypothetical? It's an idealization, because the sum of the probabilities must be equal to 1. Right? So the area under all of this curve must be equal to 1. Now how can you have an infinitely long thing and an A which is non-zero and still have the area under the curve equal to 1? You can't have that. So this is just an idealization. Anyway, the idealization is useful. Yes, please.
Sir, could we say that before the measurement it was everywhere and after the measurement it's only at one place?
Before the measurement it had the potentiality of popping out anywhere, and after the measurement we have created this quantum state, this particle, to exist at one location.
So the drag delta function is basically the wave function of the new quantum state which we...
Yes, please.
Sir, are we assuming that the particle is at a definite position inside, is it moving may not consider?
So this is a hypothetical particle that can be anywhere in space.
Quantum is not moving.
It's kind of, yeah, it's kind of everywhere. It's just there. It's idealization. But I'll come up with an example in which a particle moves. Yes, please.
So what does that inner quantum actually look like expanded out?
Which one? This one? What does it look like? It looks like this. It is this. It's a function that is just spiky. It's only existing at x naught. It's a non-analytic function. Okay? Yes, please.
Sir, for the
You can't derivate it.
Sir, for the second integral involving fx, yes, can you explain how it gives us the value of f of x and...
So if you have a function of x, suppose this is your function of x, okay, f of x. One thing is you can find the area under this, but now the function is being multiplied by a spike at x naught. So when you multiply these two functions, you get an amplitude which is the function f at x naught. And so this is your amplitude fx naught, and that just pops out because only that part of the area survives. Everything else goes to 0 because this Dirac delta function is 0 everywhere else. Okay, so this is sampling theorem. This is called a sampling theorem. All right, so let's look at another example, a more realistic example. But the free particle example is really interesting because this represents what is called a plane wave. It's a plane wave. So the free particle, even though it's an idealization, it's really important to understand the quantum physics. By the way, the question is this particle moving? Let's see. So far, this function psi, let's call it AEIKX. First of all, can you recognize what the scale is? If I look at this graph, can I identify K here? What is K? If I just look at this graph, can I tell what's K? Bolo? Yes? Sorry? No, the amplitude is A. Period. Let's not call it the period because this is space. This is the kind of distance. This is distance between these points that are on phase. In fact, it's 2 pi over k. This distance is 2 pi over k. So AEIKX is a periodic function. And you can find that if I plug x plus 2 pi over k, I'm still going to get EIKX. So the periodicity of this space dependent function is 2 pi over k. Sometimes in common language you also call this the wavelength, right? So this is just the wavelength of this free particle. Now for a free particle, this is really a quantum wave that comes with a free particle. We know that this particle can interfere itself with this quantum wave that comes with the free particle. Some people call it the de Broglie wave. Anyway, now let's sprinkle in some time dependence into this. Right? So if I just look at this part, excuse me, very important, it's going to help you. If I just look at the real part, let me just draw the real part. X. So real part. By the way, this amplitude will correspond to A. This is A. Someone said amplitude. This is A. Now, quantum physics is time dependent. The time dependent Schrodinger equation tells you. So, if a quantum state changes with time, the wave function can also change with time. So you can have a plane wave that is traveling. You can have a traveling plane wave. Suppose that plane wave is traveling. Yes, you have a question? Chalo, koi baat nahi. Doesn't matter. Doesn't matter. That's fine. Thank you. So this is the imaginary part, but doesn't matter. So now for this function, this is the wave function, and it must change with time. The wave function as I've written it is only a function of space, but quantum states change with time. So if this were a wave function, I need to have a time dependent part in it as well. Now let me write down that time dependent part, but I can motivate it. Suppose this wave, so plane wave, is traveling with a speed v. So this is a plane wave traveling with a speed v. Okay. So after some time t, what will this wave function, the imaginary part, say, will look? What will it look like? It will just be shifted. It's just going to shift in space. So this is a picture of the wave in space at some point in time. If I were to take a picture later, I had this supersonic hypothetical camera that would take pictures of wave functions. No such camera has ever been invented. But if I were to do that, if I were to take a picture of this wave function at some point later in time, this wave would have advanced forward with some speed v. And its picture might look like a shifted wave, right? So this is the picture of the wave at time t. The white one is the picture of the wave at time t equals 0. Okay, and I can do this for the real part as well, right? I can draw a picture for the real part as well, similar picture. So now can I write a function which has both a real part and a time dependent part? So I put this as a capital psi. This is convention. Wave function just with respect to position given a small psi, and when you want to incorporate both the space and the time dependent part, you want to give it a capital psi. This wave function is, by the way, ket psi in the position space, right? So this thing is this. Keep that in your mind always. So if this is the wave at time t equals 0, and I want to write a function that captures this advancing wave, advancing with the speed v, what would that function look like? I give you 2-3 minutes to think about this. No questions, no answers, just think silently. Silence is important. Think about this. Can I come up with a formula or an expression? The entire picture in all its entirety is shifting in space. That's it. The entire picture shifts. It doesn't get corrupted or deformed, just shifts. Its phase is changing, yes. Yes. अभी ओमेगा कहाँ से आ गया? वी डालो ना कहीं पे. वी की टर्म्स में बताओ मुझे. वैसे ठीक है. माइनस वी टी. Let me give you a hint. X, some function, nice smooth function fx at some point in time, if this function shifts with time to the right, so this x, so it starts off at a later x. I mean, it looks like this, right? This is at some later time. So if this function has a form fx, what does this function look like? So if this shift is, say, x naught, what does the yellow function look like? How can I write the yellow function? F of minus x naught. Good. So I advance to the right, this becomes the same function but x minus x naught. In other words, the origin has changed. Instead of x, I now have x minus x naught, and all the values will be correspondingly equal if I shift the origin. So here, in this case, what is my x naught? How much is my shift in time t? Vt. So just need to replace x with x minus vt. So I could do that. I can take this function, this one, a ei k x minus vt. Yes.
ये हमारे जो इसके अंदर x है, ये हमारे दूसरे वाले का है ना, कॉर्नर. जी, ये ऊपर f of x minus x naught है, तो x naught हमारे पहले.
यहाँ पे 0 x naught, यहाँ पे x naught है. ये पूरी चीज x naught शिफ्ट हो गई है.
x है या कोऑर्डिनेट?
ये वाला वेरिएबल x है, लेकिन ये एक डिस्क्रीट अमाउंट है x नॉट, फिक्स्ड कांस्टेंट अमाउंट x नॉट. So this is my new wave function. Got it? If the function were advancing to the left, put in a minus sign here. So this is a traveling wave, a free particle that is also traveling, so to say. Another way of writing this is, I hope you get this easy. Another way of writing this is a ei kx minus kvt. But kv is also equal to omega. So this has units of frequency. 2 pi over lambda into speed is 2 pi over the frequency, which is called omega. So I can write this thing as omega as well. These are units, dimensions of frequency, radians per second. So generally psi is ei kx minus omega t. This is a traveling plane wave or a wave function for a free particle that changes with in space and in time. And the interesting thing about this wave function is that this k, for a free particle only, by the way, we're just talking about free particles. If I take this k, the wave number, I multiply it with h bar, I get the momentum p. If I take this omega and I multiply it with h bar, what do I get? Energy. That energy is also equal to p square over 2m. So I must have this energy equal to h bar square k square over 2m for a free particle. This is as yet unknown. We need to verify this. We need to verify this. We'll verify this when we look at the time independent Schrodinger equation. So everything is systematic, nice and easy. This is the wave function for a free particle in space. Now let me come to another more realistic wave function. Suppose now I come to more realistic scenarios. This is my object, an electron. In reality, an electron is emitted from somewhere and it doesn't exist everywhere. It's emitted somewhere, like a cathode ray tube or a hot metal produces electrons. It must start somewhere. And realistically, this electron, if I just throw it, it has a trajectory. It goes somewhere. It is not totally localized, but it's not totally delocalized either. It doesn't exist everywhere. So this idealization of a free particle at best is a hypothesis. It's a useful mathematical hypothesis because it's extremely useful when we kind of look at quantum physics, but nevertheless physically it's an idealization. So we want to come up with a more realistic scenario. Suppose I draw a wave function for a more realistic scenario of a particle moving in space, and a quantum particle moving in space. X. I'm going to draw the wave function psi x in space. Okay. First of all, are you familiar with Gaussian functions? Physics lab, normal function? Of course you are. So you do recognize that First of all, let me talk about this function, a function, general function. Right? So, do you recognize this curve? It's a normal distribution or a Gaussian distribution or a bell curve. Okay? This is localized. It's concentrated somewhere and just tapers off steadily to zero far away. Okay? So this is like more realistic. It might represent a localized particle that is somewhere in the vicinity of this point x0. So this function here has a mathematical form that you may like to remember. Okay? Suppose the height is a. The height is a. So this form can be a e minus x square over 2 sigma square, where sigma, generally called sigma square, is called the variance, is this is plus sigma, this is minus sigma. So sigma plus minus sigma, 2 points on this bell curve, where the area under this curve is about 68% of the total area under the curve. Or you can also find that when I put x equals to sigma, I get e raised to the power minus 1/2. So when the value of this function goes down to e raised to the power minus 1/2, that is my sigma. So it just gives a bound, it just gives a spread of this function. Spread of the function. Higher spread, bigger spread, if sigma is large, this function becomes fatter. Sigma is small, this function becomes thinner. So this is your Gaussian distribution. This might represent a localized particle. If this function were shifted in space, then I just need to replace x by x minus the amount of the shift. Now suppose I draw a function which goes like this. And I'm drawing the real part only. Now this function that I've drawn over here is not really a plane wave, but it's a plane wave that has been multiplied with a Gaussian function. So this is the entire plane wave over here, all of it. This is your plane wave. I multiplied with the Gaussian function at the extreme right. I will get this function over here. Got it? So this function has a mathematical form. Let's call this psi x equals a eikx multiplied with this thing. Got it? So this is the function. Right? If this function were at some later point in time, this entire wave function shifts to the right, like a particle moving to the right. Then this entire wave function is displaced. Suppose at some later time its peak is at x naught. So the peak of the envelope is at x naught. So this is our new function at some later point in time. So if I were to write the wave function at this point in time, at this point in time, it's going to be A E I K x minus Vt E minus x minus Vt square over 2 sigma square. So this is a wave function that is moving, and it's also localized. This wave function is as important as the free particle wave function. It's called a wave packet, a Gaussian wave packet. This is a more realistic scenario with real particles. A particle is moving, you have this wave packet that's also moving with it. So the wave packet represents a localized wave function. It just hovers in the vicinity of the particle. Wherever the particle goes, the wave packet goes with it. So this, in 1920s, when the idea of matter-wave duality was being proposed, this is the idea that was in de Broglie's mind. That's what he called the pilot waves. So every particle carries with it, according to de Broglie, this pilot wave. This pilot wave is moving the particle. Yes, please.
Sir, if we are multiplying the function to a square, you don't have a constant.
It's a new constant. Just consider this to be new constant. All right. So this is what I wanted to talk about, wave functions. Now I would like to talk about the Schrodinger equation again. Any questions about wave functions? Yes, please.
If we were to observe this wave packet, the shape of the wave packet will change after the observation is made.
You might get a new Dirac delta function, but it's also possible that you get a new wave packet. You might get a new wave packet. By the way, in this, okay, this is a nice point. In this form, if I were to plot, it's extremely important, if I were to plot the modulus square of the wave function, suppose of this case, what would the modulus square look like?
With the negative half be reflected.
बीच वाला बहुत ज़्यादा बड़ा हो जाएगा और जो बाकी वो टेपर ऑफ हो रहे हैं वो बहुत ज़्यादा
नहीं तो वेव्स आएंगी नजर, ऑसिलेशंस नजर आएंगी. Only the envelope will appear, because remember, this is the plane wave part, this is the Gaussian part. So you take the modulus square of this thing goes away. Modulus square of EIKX is 1. So it will really be a square into the square of this. So I will just have the envelope. This is the probability density function for a wave packet. Got it? Now, yeah, thoda sa. So this is for a wave packet, the probability density function. No, all of this oscillation is washed out because it's complex. You take the modulus square, it goes to 1. This function is the modulus square of this. It's going to be a mod square E minus the square of this is minus x square over sigma square. All right. So now if I were to ask you what's the probability of finding the particle between two locations x1 and x2, what's the probability of finding the particle in this location for this wave packet? Now I need to integrate, because now this function is not a constant. The area under this curve over here, this area needs to be found, and that is found by integration. There will be some homework problems related to this. Okay, so the pink curve represents the probability density function. The area under a curve bound by 2 points represents a probability. So the probability of locating the particle between x1 and x2 after a position measurement is going to be given by dx a mod square e minus x square over sigma square from x1 to x2. All right. Now I need to find this a somehow before I'm able to find out this integral. So this a is found out by normalization. So the probability of locating the particle anywhere, that this is anywhere, correct, must be 1. So the particle must exist anywhere. If you're talking about a particle, the particle is there, otherwise we're just banging our heads against an empty wall. The particle is there, so it must be located somewhere. So this is how you find a. In the first step you want to find a, dx a e minus x square over sigma square from minus infinity to plus infinity. This integral must equal 1. वो स्क्वायर ले लिया ना, तो 2 से मल्टीप्लाई हो गया ना पावर, तो मॉड्यूलर स्क्वायर भी तो लिया है, तो जब आप इसका स्क्वायर लेंगे तो ये 2 से मल्टीप्लाई हो जाएगा ना. Alright, so this is how you find a. By the way, this is a standard integral and you need to remember this. I think it will be really helpful if you remember this integral. The integral is dx e raised to power minus some a x square, where a is positive, from minus infinity to plus infinity. This is called the standard Gaussian integral. It's very commonplace in physics. It's given by pi over a square root. Pi over a square root. So this is how you find integrals of this kind. This is a constant, you bring it out, you find the integral, equate this to 1, you'll get capital A. There will be some homework problems related to this. Yes, please. Speak up. Yeah, we can do that. Before the advent of the computer, that's how you would do it. Yes, you can do that. Now let's come to the Schrodinger equation. We've already seen the time dependent Schrodinger equation. Let's see other flavors of it. Alright. Now what I'm going to do, I'm going to write down a version of the time dependent Schrodinger equation. The time dependent Schrodinger equation, let me first write down the Schrodinger equation, the time dependent part. I h bar is d by dt ket psi. Now this is a function big psi because this has the possibility of x dependence and time dependence. So it's a function of x and of time. This equals the Hamiltonian on the ket. Now this is written in kind of ket form. So what I could do is I can take the cats and put them in the position basis. I can write this in terms of the wave function. कौन सी
e raised to power minus ax square
ये स्टैंडर्ड फॉर्म है इस इंटीग्रल की.
वो उस पूरे की a मॉडुलस स्क्वायर वो बोले
नहीं इसकी ये इसका ये आंसर आता है. इसको इस्तेमाल करके यू फाइंड दिस इंटीग्रल. दिस इज स्टैंडर्ड आइडेंटिटी.
So इसके अंदर हमारा a 1 over sigma square बन जाएगा. इसके अंदर हमारा a जो 1 over sigma square बन जाएगा.
All right. Now what I would like to do now, this is the time dependent Schrodinger equation. By the way, this is the Schrodinger equation. This is the Schrodinger equation. All right. Now I can also write a form of the Schrodinger equation that does not depend upon time. That only depends upon space. Now that form of the Schrodinger equation can be invoked. It cannot be derived, it can be invoked. So if I write this equation in terms of its eigenvalues, which is something which is not yet described in this course. So this Hamiltonian represents energy. We all know that. Hamiltonian is an operator, but the energy is a number. 5 joules, 6 joules, 1 electron volt, 2 electron volts. So what I would like to do is I would like to write this equation in two forms. First of all, I would like to replace the cats with wave functions, and I would like to replace this Hamiltonian with an energy value. Now in order to understand all of this, you need to know a little bit more about operators and eigenvalues. That's beyond the scope of this kind of modern physics class. But exactly in the same fashion as I write this equation in the cat form, which by the way I did not derive from anything simpler, I just wrote it down. You can't derive it. You cannot derive F equals ma. This is simply kind of an axiom of physics. So if I were to write this in wave function form, I h bar d by dt of the wave function without the ket. This is what the left hand side looks like. The right hand side looks like this. E, energy of the particle, energy of the quantum object, psi. All right, so far so good. Now this is this a differential equation? Yes. How many variables does it involve? 2, position and time. So far we've only looked at one variable. When we looked at the time dependent Schrodinger equation, this was just a function of time, the old version that we wrote. Okay, now we have two variables playing out together. Okay, now how do we solve an equation of this kind? The first thing that you would like to do, so this is also the time dependent Schrodinger equation. All right, the first thing that you would like to do in order to solve this, you would take this spatio-temporal function, wave function depends upon space and time, the spatio-temporal function, and break it out into two parts separately. So one part is the wave function only with respect to space, and the other part is with respect to time. So this technique is called separation of variables. Separation of variables. When you have a differential equation that has both a space part and a time part, that's the first thing you would like to do. Now if I insert this into the Schrodinger equation. Let's insert it back. So I would get IH bar d by dt of this thing. Now this has to be a partial derivative. So when I take the time derivative of this, I'm really taking the time derivative of this product. But as far as time derivative is concerned, this is a constant. So this I can just write as it is, and I'm left with dft by dt. Equals E psi x ft. Correct? When I take the time derivative, this appears as a constant, this part. Now in this equation, there is psi x on both sides of the equation. Psi x cannot be 0 because otherwise the wave function doesn't exist. There is no particle to talk about, right? So this means I can, if this is not 0, I can kind of cancel this out from both sides. Now I'm left with an equation IH bar dft is equal to EFT. You already know how to solve this. You already know how to solve this. Solve this already. So the solution to this is, can you just speak up the solution to this equation? The function of time is equal to some constant. I'm not writing down the constant. What's the solution? जिससे हमने टाइम डिपेंडेंट को सॉल्व किया था वही चीज है, e raised to power minus I e over h bar t. So homework problem, verify this for yourself. We've already seen this. We've spent about 20 minutes on this. So at least we now know that if we have a wave function, we know what the time dependent part looks like. We know what the time dependent. So our overall wave function has a space dependent part and a time dependent part. Maybe with some constant. Correct? So the time dependent part is easy. The time dependent part is just this much. E raised to power minus I energy times time over h bar. But we don't have an equation for phi as yet. We don't have that equation as yet. That equation for phi, oh sorry, psi, psi, small psi. That equation for psi, which is only dependent on x, the position, is called the time independent Schrodinger equation. And that's what we're going to do right now. Yes, please. So now you have a spatio-temporal wave function. Let me recap. Spatio-temporal wave function with a space part and a time part. The Schrodinger equation is this thing. It is this thing. So what you could do is you could find out the time dependent part of that overall wave function very easily. It turns out to be this thing. This spatial part, the space wave function, is what needs to be determined, and that comes from the time independent Schrodinger equation. Now I cannot derive this time independent Schrodinger equation, but I can invoke it or motivate it. That's what I'm going to do right now. Consider a free particle, just a free particle, the free particle has this wave function AIKX. Just talking about the space part here. All right. Suppose I take the derivative of this with respect to x. By the way, have you ever studied the wave equation, the general classical physics wave equation? Have you studied this in mechanics? No. Partial square y over partial x square is 1 over v square partial square y. So I need to write in physics. There are just 3 or 4 equations. One of them is the wave equation. The other is the heat equation. One is the Laplace's equation, and one is the Poisson's equation. Just 4 equations in classical physics. That's it. In quantum physics, there are just 2 equations. Schrodinger equation, which can also be derived from the Dirac equation. And in gravitation, there's just this Einstein's equation. That's it. Only 7, 8 big equations describe all of physics and all of the universe. So if I were to write the classical wave equation, just for your interest, the classical wave equation, partial square of some psi, let's call it psi, partial x square is 1 over v square partial square y over partial t square. This is the classical wave equation. Any wave, any classical wave satisfies this. And there's also a heat equation in which this is replaced by a single derivative and this becomes a diffusion constant. So we want to write an equation similar to this for our quantum system, for our quantum waves. So if I take this wave function, you already know that this corresponds to a free particle, a plane wave. Let me take the derivative of this with respect to x. D psi dx. What is the answer? What's the answer for this derivative? I K A. All right. If I take the derivative again of this, d square of psi dx square, what do I get? What is I square k square? Minus k square psi x. All right. Now, is this k square related to something?
Yes.
It's related to P. All right. And is that P related to something? Energy. So let's write this k square in terms of energy. Can you please do that for me for this free particle? For a free particle, for the free particle, d square dx square is minus k square psi x. This is minus p square over h bar square psi x. This is, what is the relation between E and P? P square is E over 2m. So this is minus E over 2m h bar square psi x. correct? Sorry? Sorry. Now P equals 2me, sorry. Sorry. All right. Now this thing, second derivative of the wave function equals this. I just kind of reshuffle the variables a little bit. Take this 2m over h bar square to the other side, minus h bar square over 2m second derivative of the wave function in space, this thing equals energy function. This is for a free particle. This is the time independent Schrodinger equation for a free particle, which does not see any potential energy. All right. So really what we could do is this energy, what kind of energy does this particle have? Kinetic or potential? Kinetic energy. So the energy, and here is the wave function, and here is the wave function, and I just consider this part, just this part. This is something acting on the wave function, giving me energy acting on the wave function, or energy being multiplied by the wave function. This thing, when you have this thing, what I've written in pink brackets, this is the kinetic energy. So when you want to do quantum physics, the kinetic energy becomes an operator. This is the kinetic energy. This is the operator for the kinetic energy. But if you want to include potential energy into this system as well, so I need to have kinetic energy plus potential energy to give me, this is the total energy of the system. So I need to add in a term that corresponds to the potential energy. I just do that by a sleight of my hand. I just weave this into this equation. And how I do that, minus h bar square over 2m d square dx square acting on the wave function. This is the kinetic energy part plus the potential energy part. Let's call the potential energy Vx. Could be a function of position. Now up till here we have the free particle. Now I'm generalizing this to any particle. This is the time independent Schrodinger equation. There will be homework problem on kind of, if this was the time independent Schrodinger equation, this is it in potential energy is 0. One can find out that the wave function that I've written solved this. So this is a time independent Schrodinger equation. It might be useful, though we don't like to kind of talk about memory. It might be useful to remember this. Alright, one last question. Yes, please.
Is V of x an operator as well?
Yes, where it's a multiplicative operator. So inshallah, see you on Tuesday.